Alright gang, here we go. This is for Chem 2, Unit 10. We're talking about chemical equilibrium. Alright, this stuff's very, very important. It's going to serve us well through the rest of the school year. You really got to make sure you have a good handle on just about everything we talk about in this unit. Alright, so buckle down. Here we go. Alright, concept of equilibrium. So we've already talked about this a fair amount, and we talked about it specifically when we talked about phase changes, when we were going from one to the next, or from a gas to a liquid, or a liquid to a gas, etc., etc. We talked about how we had, in order to measure the vapor pressure, we had to establish equilibrium. Okay, and so chemical equilibrium occurs when we have a chemical reaction instead of a phase change, and it happens when the reaction and its reverse reaction proceed at the same rate. Right, now that's the key right there, the same rate. So in the figure above, equilibrium is finally reached in this third picture. So here we started with only N2O4, this dinitrogen tetraoxide. All right, and it's completely colorless, and then it starts to form nitrogen dioxide, which is a brown color. And so it goes, this becomes that, and it goes blah, 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 until we eventually reach the point at which the nitrogen dioxide is forming the N2O4 as fast as the N2O4 is forming the nitrogen dioxide. All right, pretty simple. Okay, so here's just a graph of the concentrations over time. So here, and this was the start of it. We started with only N2O4 here. Okay, and then and 0 NO2, and it reached this point where we reached equilibrium. Okay, and so at equilibrium, these concentrations are no longer changing. All right, same thing happened here. Here, though, they graphed the rate instead of the concentration. So here, look at this. They took the rate equation here, K of the forward reaction and K of the reverse reaction, and then these would be the rates are based off these two reactants, right? And then here, once they've reached equilibrium at the same time, their rates are equal to one another. All right, so here they've got your concentrations, then the concentrations are not changing. And here, once again, the rates are not changing, and they are equal to each other, because that's when we've reached equilibrium. All right, so at equilibrium, the forward and the reverse reaction proceed at the same rate, and the amounts of the reactants and the reactants and the products remain constant. All right. So if you're at dynamic equilibrium, so the dynamic word, that's important. That implies that a reaction is still taking place. Just because we're at equilibrium doesn't mean our reaction has stopped. It just means that we're not changing the amounts of reactants and products as our reaction goes. All right, so the total amount, okay, of reactant product doesn't change. All right, but the key here is once we've reached equilibrium, we need to make sure that neither reactant or product can escape the system. Okay, if one of them can leave the system, then that would disturb our equilibrium, and then we would not be at equilibrium anymore. All right, so there has to be a constant ratio of concentrations. All right. So writing the equation for an equilibrium reaction, this is a lot easier in my opinion than the reaction or rate reaction loss. Okay, so since a system at equilibrium, both the forward and reverse reactions are being carried out, we write its equation with this double arrow. All right, it has to be like this, 2 half zeros. All right, do not use this reaction, this arrow. That's no good. All right, do not do that. I'll take off points. All right, so double-headed or just single-headed arrows, one above, one below, etc., etc. So you got your dinitrogen tetraoxide going to your nitrogen dioxide over to the other side. All right, so here's our reaction going back and forth. All right, if we were going to just look at the forward reaction, this would be the rate law right here. Rate is equal to Kf times the concentration of N2O4. For the reverse reaction, this was what the reaction would look like, and the rate law looks like this. Okay, now because we're at equilibrium, these two rates should be equal to each other. That's the whole point of equilibrium. That's the definition, that the rate of the first and of the reverse and forward reaction are equal to each other. So we can set these guys equal to each other. So the K of the forward reaction times N2O4 is equal to the K of the reverse reaction times NO2, and then squared, right? Because that's part of it. All right, now we could rewrite this here and put the concentrations on one side and the K values on the other side, and we come up with this new guy, capital K, okay, equilibrium. So this is the equilibrium constant. Okay, all right, and this is simply just the forward divided by the reverse rate constants. All right, and this would be equal to this guy right here. So this would be our rate constant. All right. So it would look something like this. We'd have our K EQ would be equal to, and we'd simply just write it like this, NO2 squared over concentration of N2O4. All right, and there's your equilibrium constant. All right, so we've got this other reaction, the Haber process. This is a very, very important process. This was really what allowed humanity to expand a lot more. We were able to make our own ammonia so we could make our own fertilizer. All right, and so this guy named Haber, he was probably one of the most one of the big saviors of humanity. Now, at the same time, he helped develop mustard gas and stuff like that, so he has kind of an interesting backstory. Really interesting read if you're interested in that kind of thing. All right. Anyway, so this is the Haber process, right? And you put it in a closed container, and it's going nitrogen and hydrogen will automatically start forming ammonia, and then eventually reach equilibrium. All right, and so what they did with the Haber process industrially, okay, is that they finished with this equilibrium and be able to shift it. And we'll talk about how to do that with Le Chatelier's principle here in a couple of videos. All right, but the equilibrium constant depends on the stoichiometry, and so this is really where life gets really nice. Okay, remember when I talked to you about rate constants and our rate laws, we had to do experimental processes in order to figure out what the rate law is. With the equilibrium constant, it's only dependent upon the stoichiometry. That's all that matters. Okay, so to find the equilibrium constant, all we have to do is have a balanced chemical equation. All right, and it's always, our K value generally will always be equal to the concentration of the products, all right, multiplied by each other times whatever their coefficients are, divided by the concentration of the reactants to whatever coefficients they are. All right, and that's it. So the equilibrium constant of this process here would just be NH3, the ammonia, squared, because it's got the 2 right here, and that's your product, divided by the concentration of nitrogen times the concentration of hydrogen cubed, because it's got the 3. All right, pretty easy. All right, so it says, for the reaction of this, which of the following is the correct equilibrium constant expression? All right, so we know for sure that it's got to have SO3 as a product, so that means B and A are right out because we don't have SO3 on the top, and products are over reactants. And then the other thing we're looking for here is we want to make sure that our SO2 is squared and our SO3 is squared. So these, see, they've done it wrong. Don't make this mistake. So it's got to be C. All right, products are reactants, and we use the coefficients and make them, put them as exponents. All right, and it says write the equilibrium constant expression for these guys. All right, so we'll do one of these, and I'll let you do the other one on your own. All right, so let's do A. So Kc, all right, products of reactants. So you got concentration of Hi squared over the concentration of H2 times the concentration of I2. And that's it. Nailed it. Pretty easy, right? Isn't that nice? All right, what do you start with to reach equilibrium? So look at this. This is pretty interesting. So in this specific reaction, so we're looking at this Haber process again, we started in this case with only reactants. All right, so we started with N2, that's our blue line here, and H2, that's our green line right here. All right, and so as the reaction proceeds, these start to go down, which makes sense, and the H2 is going down faster because takes 3 of them for each time this reaction completes, and our NH3 starts going up. And so this makes sense, and eventually we reach this point where we're at equilibrium, and we've got this the ratio, or these amounts of each of these, is not changing. All right, so as time goes on, these guys remain constant. All right, that makes sense. Now in the second reaction, we started with only products. All right, so here we've got ammonia with no reactants. Both the green and blue lines are at 0. Again, the reaction is going to proceed, but it's going to go in the reverse way. So NH3 is going to go down, and H2 and N2 are going to increase. Again, H2 is going to increase faster than N2 because we make 3 of those for each one N2. But eventually we reach equilibrium. All right, and notice here, once we've reached this spot, these ratios are constant, and we can look over here, can compare these values to these values, and we can see that if you just covered up the screen, all right, before the dashed line, you'd see that those ratios are exactly the same. That it didn't matter what we started with. It doesn't. It only matters what that ratio is at the end for equilibrium. That's really why we can use that stoichiometry. All right. So equilibrium constant. What is that K value? All right. So here's our generalized reaction, and so here's our equilibrium expression using this generalized reaction. Coefficients become exponents, all right, and we always use concentration, so this is our Kc, all right. Now, the Kp, we can also do it with pressures. Remember last unit we talked about how pressure and concentration are essentially the same thing because we can break down these components into partial pressures. Remember we talked about partial pressures, it's how much of the gas, or how much does our whole thing take up, or how much of the entire pressure is just the pressure of that specific component that we're talking about. All right, so we can also base our equilibrium constant off of pressures. So instead of using concentrations or molarities, we would use partial pressures. So here our Kp value, okay, is the partial pressure of D, all right, raised to the D power. So notice that it's almost the exact same setup. The only difference is instead of using concentrations, we're going to be using partial pressures. All right, so if we have both these values, we should be able to compare the two of them, and it makes it pretty easy if we use the ideal gas law. All right, we don't worry about so much all this stuff here. And so this is the equation that you need to know right here. All right, so this is just them deriving it using the ideal gas equation and so on and so forth. All right. All right, so Kp, our equilibrium constant due to pressure, is equal to Kc, our equilibrium constant due to concentration, times our R value, times T, raised to the delta N. All right, and this delta N value, this is the kicker here. This, remember, whenever we see a delta in science, we're always going to do final minus initial. So in this case, it would be products minus reactants. So it's specifically, it's the moles of gaseous product, right, minus the moles of gaseous reactants. Notice that that gaseous part is important because it doesn't make sense to talk about pressure of a solid or pressure of liquid or pressure of something that's aqueous. All right. So converting Kc to Kp says which of the following reactions is the ratio of Kp to Kc largest at 300 Kelvin? All right. Now, if we're just talking about this ratio here, then we really only talk about that delta N value. Okay. And so so it'd be like our Kp over Kc is equal to RT to the delta N, lowercase n, excuse me. Now that just looks like a squiggle, lowercase n. All right, and we could rearrange this to solve for delta n, but it's pretty easy to see that at 300 Kelvin, RT is going to remain constant. So really, whatever has the biggest delta n value is going to be your biggest. So we're just going to figure out which one is going to have our biggest delta n. So our delta n here, well, that'd be 2 here for our products minus our reactants, and they're both, so 2 minus 2, so our delta n would be equal to 0. All right, here, our delta n would be, so our product, gaseous product is 1, the reactant product is 0, so it would be 1. All right, here we've got 4 for the CO and 1 for that, so it would have 3. All right, and this guy would be 1 minus 2, so we get negative 1. All right, so the biggest would be that one. That would be the biggest ratio. Cool, cool, cool. All right, for the equilibrium, so here we're going to actually use the equation. Calculate the value for Kp. All right, so our Kp is equal to Kc times RT delta N. All right, so our Kp value would be equal to our Kc, which is 4.08 times 10 to the minus third, times our R value. All right. It doesn't really matter what R value we use because we don't really have a pressure, so we'll just use 0.0821, and we'll know our pressure is in the atmospheres. All right, 0.0821. Oops. All right, there we go. Cheating the system a little bit. Times 1,000 Kelvin. Make sure your temperature's in Kelvin. Times our delta N. Well, delta N is products, gaseous products minus gaseous reactions, so that'd be 3 minus 2. All right. So our Kp value would be equal to 4.08 e to the negative third times 0.0821 times 1,000 raised to the 1 power. All right, so I got 0.335. There you go. Boom, Bob's your uncle. All right, so equilibrium constant demonstrated. All right, so here we've got the same reaction we were talking about earlier, this dinitrogen pentaoxide reacting to form nitrogen dioxide. All right, and so they've got two different reactions, one where they've started with different reactants. Here they started with, we're looking at this nitrogen dioxide. They started with it, only this in experiment 3, and then started with 0 this in experiment 4. All right, and so at this constant temperature, our equilibrium value is going to remain the same, or this concentration is going to remain the same no matter what the initial concentrations of these two guys are. All right, and so then here they've broken down this table. So this is your experiments going across the rows. Each column is our concentrations, either our initial concentration of our two reactants or our equilibrium concentrations. And then they went ahead and did the math for us and noticed that our equilibrium constant here for all of these cases come out to be about the same value, which is pretty handy. All right, now this magnitude of our K, all right, and so this K value here, all right, is always products over reactants, right, at equilibrium. That's what we care about. All right, so if our K value is really, really big, that means our products, our numerator value, would have to be way bigger than our denominator value. So our reactants, okay, are on the bottom, so they're going to be a lot smaller than what our products are at equilibrium. So if our K value is much bigger than 1, okay, the reaction will favor the production of the products. All right, so even if you're at equilibrium, remember equilibrium does not imply that you have equal amounts. It just means that the rates are the same. So if our K value is much bigger than 1, then we've formed way more products. Okay, and then if our K value is much less than 1, that means our reactants, our denominator, was a lot bigger than our numerator. Okay, so our reaction favors forming of these reactants. All right, so so now we're going to be looking at this equilibrium constant. We're going to be talking about, well, what happens to our reaction, or what happens to this equilibrium constant as we change different facets of our reaction. All right, so all of these things, make note of these because these will be important moving on. All right, so this is kind of a bunch of tools in your tool belt is what we're going to cover right now. All right, so the equilibrium constant of reaction, the reverse, is the reciprocal. Okay, is the reciprocal of the equilibrium constant of the forward reaction. Remember, reciprocal just means the inverse. All right, so we've got in this reaction here, okay, our equilibrium constant, our equilibrium expression would look like this. Products over reactants, NO2 squared over N2O4, and then it would be equal to this value here. Now, if you're going to do the same reaction here, all right, but you're going to look at it the opposite way, okay? There's no reason why you can't do that. I mean, it's just the reaction just flipped, but it's all taking place in the same container. So it doesn't really matter if one's forward and one's reversed. So if we do it this way, our equilibrium expression would be simply upside down of what we had before. It'd be N2O4 over NO2 squared. And so then in all of these two things, the only thing that's different is that it's flipped. So it would be the inverse of that. So if you took 2.212 and took the inverse of that, you get 4.72. All right. So if you reverse your chemical equation, all right, then your equilibrium constant is just inversed. It's just the reciprocal. All right. So let's see. Oops. Here we go. All right, let's skip this one here up here. All right, never mind. All right, let's do it. The equilibrium constant for the reaction N2O4 is equilibrium with 2NO2. All right, so we're used to this one at 2 degrees Celsius. Kc is equal to 2.0. If each yellow sphere represents 1 mole and each brown sphere represents 1 mole, which of the following 1 liter containers represents the equilibrium mixture at 2 degrees Celsius? All right, so all we have to do is look at these guys and figure out what their K value would be. All right, so our Kc would be equal to NO2 squared divided by the concentration of N2O4. So all we have to do is plug in each of these guys. The brown spheres are NO2. All right, so for this guy specifically, our Kc value would be equal to 1, 2, 3, 4, 5, 6, 7, 8 would be 8 squared over 1, 2, 3, 4 over 4. All right, I'm not going to write this out for all of them. But so 8 squared divided by 4, and we get 16. So that one's right out. Okay, because it has to be, our Kc, if we're at equilibrium, should be equal to 2. So this one's no good. All right, so let's try this one. So this one would be 1, 2, 3, 4. So this would be 4 squared over 1, 2, 3, 4, 5, 6, 7, 8. So 16 divided by 1, 2. What? 4 squared divided by. Wait, 1, 2, 3, 4, 5, 6, 7, 8 divided by 8. Oh my goodness, my brain just hiccuped hardcore. So it would be 16 divided by 8, so that would be 2. All right, so this is probably it right here. All right, we can check the other ones, just make sure our pattern's working out here. 1, 2, 3, 4, 5, 6. So this would be 6 squared over 1, 2, 3, 4, 5, 6 over 6, so that's going to be equal to 6. All right. And then 1, 2, so that'd be 2 squared divided by 1, 2, 3, 4, 5, 6, 7, 8 over 8, so that'd be 4, so that'd be equal to 1/2. That's no good either. And cross those guys out. And then this one, 1, 2, 3, 4, 5, this one's not going to work either. All right, so it's got to be B. B's our answer here. For the reaction of this, H2 plus I2 yields 2HI. Kp is equal to 794, and Kp equals 55 at 700 Kelvin. Is the formation of HI favored more at higher or lower temperature? So HI, if it's favored, that means our K value should be really big. All right, so this one here is much bigger. And we say we want it to be really big because remember our K value is products over reactants. All right, and so when our K value is really big, that means our products are favored. Okay, and so that 794 means our products are favored right there. So it'd be favored at lower temperatures because 298 is lower than 700. All right. A couple more things in your tool belt here. To find the new equilibrium constant of reaction when the equation has been multiplied by a number, simply raise the original equilibrium to that power. Here, the stoichiometry is doubled, so the constant is squared. All right, so this makes sense again. If this was our reaction, this would be our equilibrium expression here. All right, if we just multiplied all of these coefficients by 2, okay, then we'd simply raise all these guys to the second power. So the 2 would be squared and become 4, and then the 1 would be squared and become 2. All right, and then so really all that we did was just raise the equilibrium constant to the second power. All right. And this one's the last one, and this one's kind of more confusing than the rest, okay? If we're going to have 2 consecutive equilibria that are making up our total reaction, then our equations must be added together to give a single equilibrium. All right, so the equilibrium constant of the new reaction is the product of the 2 constants. So if we had some overall new reaction, and these are the original 2 equilibriums that went into making this one, we take the first times the second. So for example, we have this guy here. We have 2NO-Br is in equilibrium with 2NO and Br2, and then that Br2 is being used in this equilibrium. All right, so you could almost look at this as a reaction mechanism a little bit. All right, and so if our overall reaction was simply just taking these 2 together, our Br2s would cancel, and we'd have 2NO-Br plus Cl2 as an equilibrium with 2NO and 2BrCl. All right, so that makes sense. So in order to get this overall equilibrium, we would simply take our K1 value times our K2, and so our K over this new reaction here, K3, all right, that would be equal to this guy right here. Right. Last thing here, okay, homogeneous versus heterogeneous equilibrium. Homogeneous equilibrium is when all the reactants and products are in the same phase. So everything is gaseous, everything's aqueous, everything's solid, etc. Heterogeneous equilibrium occurs when something in the equilibrium is in a different phase. All right, so if you have a solid mixed in with gases, or if you have aqueous mixed in with gases, okay, and so anytime you have the concentration of a pure substance, the concentration is always equal to 1. All right, and so so all solids are just 1, all liquids are just 1. Okay, yeah. So if you have this reaction here, calcium carbonate is decomposing to form calcium monoxide and carbon dioxide. Because the calcium carbonate and the calcium oxides are solid, they just become 1 in your equilibrium expression. So your equilibrium expression would be something like this. It would be Kc. If we were going to ignore that rule here for a second, it would look like the concentration of calcium monoxide or calcium oxide times the concentration of CO2. All right, over the concentration of CaCO3, calcium carbonate, and we can see that these guys are solid. Well, what would be the concentration of a solid? Well, it's moles per liter of the solvent, moles of the solute over liters of solvent. Well, they're the same, right? And so this guy would just become, this is just 1, and then this would become 1, so the Kc would just be equal to the calcium or carbon dioxide. All right, and so here's your Kc value, and here's your Kp value. And notice that they're exactly the same, just like we talked about earlier. And that's it. I know it was a long one. My voice is tired. I'm sure you're tired of sitting. So do your practice problems. Let me know if you have any questions, and I'll see you on the flip side.